So next we have part C of our exercise. In this part we have to show that this pair is complete. In the previous video we have already shown that this dx bar is a metric on x bar. So that means this is the metric space. Now here we have to prove that it's complete. That means every Cauchy sequence of points in this space will converge to some limit which is in this space itself. Solution: let this be a Cauchy sequence in x bar. Do not forget that the elements, the points in x bar are formal limits of Cauchy sequences in x. So here, for each positive integer n, this xn superscript m, where n varies from 1 to infinity, is a Cauchy sequence in x, and its formal limit you are seeing here. So this is a Cauchy sequence of such formal limits where the terms, you get the terms as you vary this m from 1 to infinity. Now we need to prove that this entire sequence converges to some point in x bar. That means that point will also be a formal limit of some Cauchy sequence in x. Now because each such x and m is a Cauchy sequence in x in the original metric space x, so that is why for each such m there exists a positive integer in m such that the distance between these two terms of this sequence for that m, which correspond to the suffixes n1 and n2, is less than 1 divided by n for all n1 and n2 greater than or equal to that positive integer nn. Now you consider this sequence ym, where m goes from 1 to infinity in the original space x, where ym is xnm superscript m. That means it is that term of the sequence xnm where the suffix is this nm, that positive integer. We claim that this sequence ym is itself a Cauchy sequence. Let's first prove that. And to show that, we choose a positive real number epsilon 1. And now we recall our hypothesis that this is a Cauchy sequence in x bar. Because of this fact, there exists a positive integer n such that the distance between the pth term and the qth term of this sequence of formal limits is less than epsilon 1 divided by 3 for all p and q greater than or equal to that positive integer n. However, recall that this distance by definition is this limit as n tends to infinity of the distance between xnp and xnq. Okay, so this is something we have got from the fact that this is the Cauchy sequence, which is our hypothesis. Now, if for some p and q of this type, that means you fix p and q for which infinitely many terms of this sequence, the sequence that you see here, whose limit you are seeing here, infinitely many terms of the sequence are all greater than or equal to epsilon divided by 3. Then they would form a convergent subsequence whose limit is also greater than or equal to epsilon 1 divided by 3 by the comparison principle. Why would they form a convergent subsequence? Because they form a subsequence of this sequence which already is convergent, because its limit we were writing there. That is why. But that would contradict this inequality which we already have, which you saw here just now, that the limit of this entire sequence is less than epsilon 1 divided by 3. So how can it have a subsequence which converges to a limit which is greater than or equal to epsilon 1 divided by 3? Due to proposition 665. What was this proposition? It says that if you have a convergent sequence, then in it every subsequence is convergent and converges to the same limit. So that means this cannot happen. So for each such p and q, there exists a positive integer in suffix p comma q. To show the dependence of this on p and q, we have written like this, such that this distance is less than epsilon 1 divided by 3 for all n greater than or equal to this y. What did we show there? that sequence whose terms look like this, that sequence of real numbers cannot have infinitely many terms where all the terms are greater than or equal to epsilon 1 divided by 3. So that means at most finitely many such terms can be there, are possibly there. So if you go far enough down the sequence, you will get a stage after which all the terms are less than epsilon 1 divided by 3. And this will happen for any such P and Q. That's why we have this. Next, let K be a positive integer which is greater than 3 divided by epsilon 1. Obviously, there will exist such a K because positive integers have no upper bound in the set of real numbers. So no matter how small epsilon 1 is, and as a result, this 3 divided by epsilon 1 can be quite large. But even then, there is a larger positive integer K. All these things may look very arbitrary and without rhyme or reason, but we will see why we need this K. Next, let L be the capital L be the maximum of NP, NQ and NP, Q. Don't forget that this NP is one of those NMs that we had in the beginning itself. Now next we take any two integers P and Q greater than or equal to the maximum of K and N. K is this K and N we previously got, and for this P and Q we considered the distance between YP and YQ. YP is XNPP and YQ is XNQ superscript Q. And then we apply the triangle inequality 2 times and get that this distance is less than or equal to the distance between XNP P and XLP plus the distance between XLP and XLQ plus the distance between XLQ and XNQ. Okay. Now the first term is less than 1 divided by P. So it is coming from that inequality where you had 1 divided by small n. It's from there that we are writing this. But can we write this? Well, for this to be true, the suffixes should be at least NP, this NP. NP is at least itself, it's greater than or equal to itself. What about L? Yes, L is also greater than or equal to NP because it's the maximum of these three numbers, these three integers. So that means this is really less than 1 divided by P. Similarly, the third term is less than 1 divided by Q. Here the condition is that the suffixes should be at least NQ. This is okay, and L is also greater than or equal to NQ because NQ is present here. And the middle term is less than epsilon 1 divided by 3 because, and for that to be true, we need the suffix, which in this case is the same, to be at least NP, Q. Yes, L is greater than or equal to that also. Okay, now where do we go from here? 1 divided by P is less than or equal to 1 divided by K. Why? Because P is greater than or equal to K. That's why. Similarly, Q is also greater than or equal to K. So 1 over Q is less than or equal to 1 over K. However, K has been chosen like this. K is greater than 3 divided by epsilon 1 if you take reciprocal on both sides because these are both positive. So you will get the fact that 1 divided by K is less than epsilon 1 divided by 3. Now adding these 3 epsilon 1 over 3's, you get epsilon 1. So what is it that you have got here? You have proved that for any epsilon 1 which is positive, there exists a positive integer maximum of K, N. We need not see maximum of what, after all this is a positive integer such that if P and Q are at least, both of them are at least this much, then the distance between YP and YQ is less than epsilon 1. That means this is a Cauchy sequence. So we write the conclusion like this. This proves our claim that Ym, where m goes from 1 to infinity, is a Cauchy sequence in the original metric space X. And because of this fact, the formal limit of yn, which makes sense, will be a legitimate point in our new metric space x bar. Now the next claim would be to prove that the Cauchy sequence we started with, where each term is a formal limit, actually converges to this point. So we next claim this. This is a general term of our Cauchy sequence of formal limits with which we started the solution. We want to prove that this sequence, where the index is m, itself converges to this formal limit. To prove this claim, choose a positive real number epsilon 2 and choose a positive integer m1 greater than 4 divided by epsilon 2. Since the sequence ym is Cauchy, which we showed there exists a positive integer m2 such that the distance between ym and yn, the mth and nth terms of the sequence, which is nothing but this, the distance between x nm superscript m and x nn superscript n is less than epsilon 2 divided by 4 for all indices m and n greater than or equal to m2. So for each small m greater than or equal to the max value of capital M1 and capital M2, we consider the distance between xn superscript m and yn. Yn is this x suffix nn superscript n. And then we use triangle inequality and push this extra term in between, which is xnm superscript m. We already of course have this one and this one. Okay. But suddenly a confusion arises. I have said what this small m is. Small m is like this. But what is this n? I haven't said anything about n. I am coming to that, okay. Now this first term is less than 1 divided by small m, but there is a condition. You already know that. This will happen when this and this are both at least nm. Nm is greater than or equal to itself, it is at least itself, but I need this small n to be greater than or equal to nm, which I haven't written. That means I have to write that. But assuming that I have considered that, that is there with us, this is less than 1 divided by m. And the second term is less than epsilon 2 divided by 4 because of this. However, m and n should be greater than or equal to m2, right? Because then only this happens. So is m greater than or equal to m2? Yes, we already have that. M is greater than or equal to the maximum of m1 and m2. So obviously m is greater than or equal to m2 also. But I need n to be greater than or equal to m2 as well. So I need n to be greater than or equal to m2, and for this to happen I need n to also be greater than or equal to nm. So accordingly now I have to write it. But before we write that though, let us take this calculation to its conclusion. This 1 over small m is less than or equal to 1 over capital M1. Because small m is greater than or equal to m1 also, that is why. And you go back and see how we chose this m1. m1 is greater than 4 divided by epsilon 2. So 1 divided by m1 will be less than epsilon 2 divided by 4. So that's how we find that this distance is less than epsilon 2, but with a condition. And that condition is this: whenever small n is at least nm as well as m2. This means that for each such small m greater than or equal to maximum of capital M1 and capital M2, all the terms of this sequence dxn m, yn as n varies from alpha to infinity, where alpha is this max of nm, m2, because for small n greater than or equal to this type of alpha, only the previous calculation is true. So what are we saying here? That all the terms of such a sequence will satisfy the following inequality. that all the terms are less than epsilon 2 divided by 2. There is a mistake in the previous calculation. There I foolishly wrote epsilon 2 divided by 4 plus epsilon 2 divided by 4 equal to epsilon 2. No, it is epsilon 2 divided by 2. Okay, so you please rectify that. You will understand now why I chose 4 there in the denominator. So by lemma 6 for 13, which is our comparison principle, the limit of this sequence, which we already know exists, is less than or equal to epsilon 2 divided by 2. Note carefully that the comparison principle gives us ordinary inequality, not strict inequality. Okay. But there is a slight problem. Here we are not really saying anything about how this n varies. N does not necessarily go from 1 to infinity, rather n goes from alpha to infinity, and this alpha depends on m. But here exercise 613 saves us, which says that if you have a sequence of real numbers, then removing finitely many terms from it does not affect its convergence. If the original sequence is convergent, then the removal gives us a subsequence which will also be convergent and converge to the same limit. And if the original sequence is divergent, then the removal again gives us a divergent sequence. So by that, here we need not worry about how n varies or from where n starts. So we have this thing which is less than epsilon 2. So it is to get this strict inequality that I chose 4 there, so that we have epsilon 2 divided by 2, and then we can get strict inequality, because I knew that I had to use this one, so which will give me ordinary inequality, that's why. However, this limit is nothing but the dx bar distance between this term of what? This is a general term in the original Cauchy sequence that we started the solution with. That here m is what changes. Okay, so it is that sequence of formal limits, the distance between this one and this single formal limit of yn, which already exists, that we showed in the first half of the solution. This is less than epsilon 2 for all m greater than or equal to maximum of m1 and m2. So what have you found now? Is this not claim 2 which has been proved? For any epsilon 2 greater than 0, you have found a positive integer maximum of m1 and m2, such that if your m is greater than or equal to that, then the distance between the mth term of that sequence of formal limits and this formal limit is less than epsilon 2. So what does that mean? It means that this sequence converges to this. I think it's going to rain. You may hear some thunder and some noise disturbance will be there, okay? Cannot do anything about it. So let's write the conclusion. So this is our conclusion. This proves the second claim, i.e. limit of this sequence of formal limits as m approaches infinity equals this formal limit of yn. So we wanted to show that this Cauchy sequence converges to something in x bar. That something is this. So that means every Cauchy sequence is convergent. That's why this metric space is complete. And here the solution ends. Solution to part C only, okay. I think there still is D, and then after that we have E also. 2 more parts.